All right, so our first lecture is going to be on acids and bases. So we're going to talk about what an acid is, what a base is, how acid-base reactions work, and some of the fun things that we can do with acids and bases and calculations, and how they can be useful to us. All right, so let's talk about some properties of acids. Um, First of all, they have a sour taste. That doesn't mean you want to taste them. They can dissolve a lot of metals. So we can see a lot of metals dissolve in acid HCl, and that actually creates a gas evolving reaction, which we talked about in first semester. So something like zinc dissolved in hydrochloric acid can create zinc chloride and hydrogen gas. It can neutralize bases, so that's a big one. An acid is something that can neutralize a base, and when we have an acid and base that react together, we get an acid-base neutralization reaction, which we also discussed last semester. And then one way we use, or one thing we use to determine whether or not we have an acidic or basic solution is something called litmus paper. And litmus paper is a pH-sensitive paper that will turn blue in the color of a base and red in the color of an acid. So if you have blue litmus paper and you're testing for an acid, it can change it red. Here's a table of common acids. I will expect you to know all of these acids. So hydrochloric acid is a really common strong acid. It dissolves a lot of metals. People use it in food preparation. Sulfuric acid is also a really common acid. It's used in explosives manufacturing, dye, glue production, fertilizer. Nitric acid is also a good acid for dissolving metals. So a lot of metals will dissolve in nitric acid to create metal nitrates. We also use nitric acid in fertilizers and explosives. Acetic acid is a weak acid. That's just vinegar. If you go to the grocery store and buy some vinegar, it's diluted acetic acid. And we use it in food preservation commonly. Citric acid is also used in food preservation. It's an acid that we naturally find in fruits. And carbonic acid is one that we find in the ocean quite a bit when we have ocean acidification. So when CO2 dissolves into ocean water, we can get carbonic acid, which lowers the pH of the ocean, makes it more acidic. Hydrofluoric acid is a really nasty acid. People use it to clean metals and glass. It's a weak acid, but it's a very reactive acid. And then phosphoric acid. Okay, now we can categorize these acids in a bunch of different ways. The first of which is a binary acid. So a binary acid is anything that just has two components to it. So if you look at our molecule up here, we have H and Cl. So we only have two components there. And a lot of binary acids are things like HCl, HF, HBr. And then, of course, we also have oxyacids. Oxyacids are anything that have the acidic protons attached to an oxygen. So, let's go back to our binary acid for a moment. Whenever we have an acid, we always write the acid. So the hydrogen, the proton, is written first. That's the proton that comes out. So if we were to take HCl and put it into solution, what would happen is it would dissociate, and that hydrogen would come off to create a proton in solution, and we would also get chloride, right? I know it's not a very good hydrogen here. We'll remake that. So the reason why we call that a proton, this hydrogen that's out there first, we call it a proton because it essentially dissociates immediately when you put it in water. And if you have a hydrogen dissociated in solution, really all it is a proton, because it gives its electron up to chlorine. So what really happens here is that one electron hydrogen has, it's gonna donate that baby to chlorine, and that's gonna make chloride Cl minus and leave us with proton H plus. So whenever we have an acid, we always write the acidic proton is the proton that dissociates, right? It's this first proton written in an acid. That's what we mean when we say acidic proton. So when I think about an oxyacid, an oxyacid has the acidic proton now attached to the oxygen. So if we look at this molecule, our acidic protons are here and here for H2SO4. And we write those two acidic protons first in the acid formula. Now for nitric acid, HNO3, right, that acidic proton which is written first is right there. So the definition of an oxyacid is an acid where the acidic proton is attached to an oxygen molecule. All right, now we also have carboxylic acids, and I think we discussed carboxylic acids a little bit in class. Our oxyacids are defined as any type of acid where the acidic proton is attached to an oxygen, and then that oxygen is attached to another atom of some sort, like a sulfur or a nitrogen. For a carboxylic acid, it's still a type of oxyacid where the proton here is attached to an oxygen, but now that oxygen is attached to a carbon which has a double bond O. So this is like an alcohol, right? You can think of this as an alcohol group attached to a C double bond O. And because it's attached to the C double bond O, it really weakens this oxygen-hydrogen bond, and it makes that hydrogen like a proton, and it's acidic, so it can lose it really easily. All right, so what happens in a carboxylic acid is, we can have something like citric acid or malic acid, where we have several protons. Citric acid takes this formula right here. So we have 3 acidic protons. We write those 3 acidic protons out in front. So we would call that a triprotic acid, right? So that's a triprotic acid because we have 3 protons. Now this is acetic acid, vinegar, which only has 1 acidic proton out in front. So that's a monoprotic acid. And then malic acid is a pentaprotic acid. It's actually got 5 carboxylate groups, and it can lose all 5 of those hydrogens. Okay, so even though we have this COOH group, so we can write this carboxylate as COOH, the hydrogen off that COOH group, that's the acidic hydrogen, and that's the one we typically put out in front. Just for nomenclature's sake, we always list that acidic proton there first. Okay, so what about bases? Well, a base is anything that tastes bitter, although you don't want to taste it. Actually, bases are a lot more dangerous than acids in a lot of senses. But a lot of plant products contain mostly basic nitrogen atoms. So nitrogen atoms can serve as bases. They can be poisonous, and they can lead to birth defects. So you definitely don't want to go around tasting any kind of base just to see, oh, this is sour, or this is bitter, I know this is an acid or base. That's not a good barometer for classifying these things. One example of a plant form of a base is cyclopamine, and it's introduced through the corn lily plants. So this is a steroidal alkaloid, which means it's a steroid base, and what happens is it actually inhibits something called the hedgehog signaling pathway. So this was found out in Montana, and they discovered that they were getting deformities and birth defects in the goats out there. So the image over there is the head of a defective goat that was born, and you can obviously see it's got some problems with having one eye like a cyclops and a foot going off the forehead and in the mouth. And what they discovered was that the goats out there were eating a lot of corn lilies when they grazed, and this molecule, cyclopamine, was doing the damage. It was inhibiting this hedgehog signaling pathway, which influences the balance of active and inactive smoothen protein, and that smoothen protein is responsible for giving you symmetry when you're being made from a fetus. So they were having birth defect issues in the goats out there, and they linked it back to this plant and this steroidal alkaloid. They also feel pretty slippery, and if acids could turn blue litmus paper red, well, bases can turn red litmus paper blue. And of course, they can neutralize acids. So here's a table as to common bases that you can look at. These bases are sodium hydroxide, potassium hydroxide. Those are both strong bases. We use sodium hydroxide quite a bit. It's also referred to as lye. So it's used in making soaps. That's one interesting thing you might be thinking about now is using soap, washing your hands. Well, sodium hydroxide is an important component in saponification. Soap's basically just a formation of a lot of fatty acids, things like fat acids through olive oil and coconut oil, and they polymerize by reaction with sodium hydroxide to harden into that hard bar of soap. You can also use potassium hydroxide for this process, but we use potassium hydroxide in a lot of other things, such as batteries and electroplating. Sodium bicarbonate, that's basically baking soda. It can act as a weak base. It can also act as a weak acid, and we'll talk about that later on, how you have substances that can act as acids or bases. And sodium carbonate, and then of course ammonia. Ammonia is an important component of fertilizer, and that's what we call an amine containing compound. So anytime you have a substance that has a nitrogen in it, an NH3 group or an NH group of any sort, we call that an amine. All right, and most amines are bases, and ammonia is the simplest of the amine bases. So the three definitions of an acid and base that we work with are the Arrhenius definition, the Bronsted-Lowry definition, and the Lewis definition. So the question is, how can you determine what's an acid and what's a base? Well, over time, people tried to define what it is. And as our understanding of chemistry got better and better, our definitions got better. And so we're going to look at all three of these definitions. The first of which is the Arrhenius definition. The Arrhenius definition is the most simplest form of the acid-base definitions we have, where it just says an acid is anything that dissociates to create an H plus in solution, and a base is anything that dissociates to create an OH minus in solution. So if we think about a simple binary acid like HCl, it's pretty obvious that HCl forms H plus and Cl minus, and that gets us our definition of an acid, right? We're forming H plus in solution. Likewise, if we take a strong base like NaOH, right, and these are all aqueous, when we put it in water, we should get sodium plus and OH minus, because it will readily dissociate. So now we fit our definition for the Arrhenius acid and base. But what happens in the case of something like ammonia, NH3? Well, it becomes a lot more difficult because there's no hydroxide there. We know it's a base, so the Arrhenius definition doesn't really hold up here. So we had to develop better definitions, and one definition we developed that was better was the Bronsted-Lowry definition. The Bronsted-Lowry definition said an acid is a proton donor. And as a proton donor, it increases the concentration of H3O plus in aqueous solution. A base is a proton acceptor that increases the concentration of OH minus in solution. All right, so these definitions, the Bronsted-Lowry definition was much better. And essentially what it's doing is that giving us a more realistic look at what's happening in solution. So what we could do here, right, if we think about HCl in solution, what really happens, it doesn't just lose that proton. It actually reacts. So if we have HCl, it's loosely bound to the chlorine atom here. And if you put it in water, right, it actually is going to react with the water. The structure of H2O, the Lewis structure, looks something like this, where we have two hydrogens attached to an oxygen, and there are two lone pairs of electrons. Well, those lone pairs of electrons can actually get a little greedy, and they can come in here and they can grab that proton. And when that happens, the electrons in this bond get donated entirely to chlorine. So in this event, right, the water is picking up the proton from HCl, and now we're creating H3O plus. and Cl minus. Okay, so that, oh, sorry for that. Let's go back to what we were dealing with there. So that, there we go. That, can't put my bracket in. There we go. That Cl minus, right? This H3O plus, this is known as the hydronium ion. Okay, and the hydronium ion is actually what gives us the acidity in solution. So this is synonymous with also writing HCl AQ dissociating to H plus AQ and Cl minus AQ. So we use H plus and H3O plus synonymously, and we just say, look, these two are the same thing. So when you write H plus, what you really mean is hydronium ion. Now, this top reaction up here, right, this one up here that I'm highlighting in blue, that's actually the more accurate. That doesn't look very good. Let's try this again. Let's highlight this in a different color. All right, so this reaction up here that I'm highlighting, that's the more accurate reaction. That's what really occurs. So this is just kind of a shorthand way of doing it, so we'll just erase that. It doesn't matter which one you use. You know, I prefer to use the top one because it's a more accurate depiction of the chemistry that's actually occurring in solution. Now, if you think about bases, this makes a lot more sense because we can say, okay, well, a base is anything that is a proton acceptor, and it increases the concentration of OH minus in solution. All right, so what happens in that instance? Well, if you think about something like ammonia, right, we have NH3. How is this thing a base? Well, according to the Arrhenius definition, it's not a base because it doesn't dissociate to give OH minus. But remember, ammonia's Lewis structure looks like this. We got 3 hydrogens attached here, and we've got a lone pair of electrons on top. So this creates a tetrahedral electron geometry, which gives us a trigonal pyramidal geometry. And because of that lone pair, it gives us a trigonal pyramidal geometry. These electrons are very reactive. As such, they can pick up a proton. So if you put this thing in water, right, what'll happen in water, and this is our structure of water, we just saw how water picked up a proton from HCl. Well, now it's going to donate a proton. All right, and the nitrogen from ammonia will pick that hydrogen up, pick that proton up, donate the electrons back to oxygen. And when this happens, what are we going to be left with? Well, we're going to make ammonia, NH4 plus, and hydroxide. So now we can see how this acts as a base. We are increasing the concentration of hydroxide, right? Now we fit that Bronsted-Lowry definition. So before, ammonia is not an Arrhenius base by definition, but it is a Bronsted-Lowry base by definition. And another thing you might have picked up on that's really interesting is the fact that water has acted as an acid in one instance and a base in another instance. So, you know, these acids and bases are complementary properties. Think about our Bronsted definition. An acid is a proton donor that decreases the that increases the concentration of H3O plus in solution. All right. So what's going on here? Well, if ammonia is our base, water is acting as an acid here. It's donating a proton to ammonia. And when you have HCl, the opposite occurs, right? HCl acts as an acid. Well, water is acting as a base to pick up that proton. So this property in water is called amphoterism. So we say this is amphoteric. All right, this is an amphoteric substance. And that just means it can act as an acid or a base. All right, it has the ability to act as both. Okay, let's go back to our slide. We still got to go over the Lewis definition. The Lewis definition, the third definition on here, is the most accurate definition we have because it really works for all forms of chemistry. And it says an acid is an electron pair acceptor. A base is an electron pair donor, right? So if you think about it's kind of the opposite of the Bronsted-Lowry definition. Bronsted-Lowry focuses on H3O plus in solution, OH minus in solution. It says an acid is a proton donor, a base is a proton acceptor. Here we have the opposite. The acid is an acceptor, but it's not accepting the proton. It donates the proton by accepting the electrons. So if we go back to that reaction we have with ammonia or with HCl, right? Think about what happens with HCl. We have HCl and we have water. And I'm just going to draw a set of lone pair on the electrons on the water there. That lone pair picks up the proton. So it is donating electrons to HCl, right? And HCl is accepting electrons. So we would say that this is my electron acceptor and this is my electron donor. So that fits our definition really well because our Lewis acid is the electron acceptor, our Lewis base is the electron donor. And if you think about the Bronsted-Lowry definition, it also works there because the acid is donating a proton. By accepting those electrons, right, the proton goes from HCl to H2O to create H3O plus and leave behind Cl minus. So in this instance, HCl is acting as a Lewis acid. It's acting as a Bronsted-Lowry acid. It's also acting as an Arrhenius acid. Okay. Now, the reason why the Lewis definition is the most accurate form is because it is not dependent on H3O plus, right? The only thing the Lewis definition does is it focuses on electrons, okay? And that is extremely important because we have substances that are aprotic, okay? And those are acids that don't have protons. So you can have acids that don't have protons on them. And if you have an acid without a proton, well, how does it fit Arrhenius and Bronsted-Lowry? It doesn't. But an acid without a proton still can have electrons that can be donated or accepted, right? And so if you're accepting electrons, that means you're a Lewis acid. And just because you don't have a proton doesn't mean you can't be an acid. So the Lewis definition is kind of the all-encompassing definition because it focuses on those electrons, not just the proton. All right, so here's an example of our Arrhenius acid. You can see H plus in solution. It's increasing that concentration. Here's our example we looked at earlier with sodium hydroxide, just a visual representation to show you it's a dissociation. So if you look at the Arrhenius definition, you're really thinking about dissociation more. And H plus is actually H3O plus in solution, but we use that term interchangeably in chemistry. And so if we look at Arrhenius acid base reactions, we could say, well, when you mix an acid and a base together, the proton from the acid combines with the hydroxide from the base, and that's going to make water. And we talked about acid-base neutralizations last semester, and we said, look, anytime you have an acid and a base, you mix it together, you always make water and salt. So if we think about that reaction of HCl and NaOH together, what's going to happen? Well, in solution, right, both of those substances are going to exist as H plus and Cl minus, Na plus and OH minus. So what's going to happen is whenever you have an H plus and an OH minus together, they're going to react to form H2O. And what do we leave behind? Well, we leave behind sodium ions and chloride ions. That creates an electrostatic interaction, and we get NaCl. So our full reaction of HCl plus NaOH is the sodium chloride, salt, and water. All Bronsted acids are also Arrhenius acids, but not all Bronsted bases are Arrhenius bases. So ammonia is the big exception that we notice right there. And for the Bronsted definition, we're really looking at the reaction. We're not looking at the dissociation. It's more the reaction that occurs with water. And so we can think about this reaction as an equilibrium. We just talked about how everything's in equilibrium to a certain extent. But for a lot of acids, the equilibrium pushes so far to the right that we consider it single arrow. And if we think about a Bronsted-Lowry acid-base reaction, well, we have an acid of some sort, which I've labeled as HA here. So this is our acid, okay, and B, that is our base. And what happens is we make A minus and HB plus. So we could look at the reaction of water with HCl, which we just looked at, and we say, okay, what's acting as the acid or base? Well, water, and we're looking at this from the standpoint of the proton, water is accepting the proton, right? Bronsted-Lowry theory looks at where the proton goes, not the electron, and the proton moves the opposite of the electrons. So water is accepting the proton, HCl is donating the proton, so that makes HCl our acid, and it makes water our base in this instance, okay? But if we think about this, our forward reaction, right, is HA plus B minus. So we would say, okay, this is our forward reaction. H2O gives us H3O plus and Cl minus, right? So that's forward. We could also look at this in the reverse if this is the equilibrium. And in the reverse, we would have H3O plus plus Cl minus, and that would make H2O and HCl. So we just talked about in the forward reaction how water is accepting the proton, so it's acting as our base. But in the reverse reaction, what's accepting the proton? It's Cl minus. Okay? So both of those substances are acting as a base in the forward and the reverse reaction. Now, what about the acid? Well, the acid is a proton donor. So in the forward reaction, HCl is donating the proton, but in the reverse reaction, hydronium, H3O plus, is donating the proton. So what we've done is we've said that, okay, we can have an acid and base in the forward reaction. We can also have an acid and base pair in the reverse reaction, right? So these acid-base reactions are reversible in a Bronsted-Lowry theory, which is really important. And this creates conjugate pairs, right? So this is the important thing we want to get to, is a conjugate pair. So in the forward reaction, we have an acid, and that acid in the reaction we looked at is HCl. By donating its proton, it creates something that will act as a base in the reverse. That base is Cl minus. So we would say, okay, the acid then is HCl, and its conjugate base pair is Cl minus, right? So every acid and every base has a conjugate pair that is complementary, okay? So if we think about this reaction, that's our HCl is our acid, Cl minus is our conjugate base. Well, if H2O is our base, right, what is the conjugate acid pair? It is H3O plus, okay? And so our acid is defined as a proton donor in the forward direction. The base is defined as the proton acceptor in the reverse direction, or in the forward direction. The conjugate acid-base pairs have the same definitions but apply to the reverse reaction. So the conjugate base Cl minus is here. It's a proton acceptor. It acts like a base in the reverse reaction. The conjugate acid H3O plus, that's a proton donor in the reverse reaction. It acts like an acid. Okay, so that's how we come up with these conjugate pair definitions. right? So HCl, Cl minus, those are our conjugate pairs. And then H2O, H3O plus, that is another conjugate pair. All right. What about the reaction with ammonia? I want you to take a moment to stop and identify the acid and the base, and also the conjugate acid and conjugate base pairs. Go. All right, so if we think about this reaction, we have to consider where the proton's going. And we say, well, I'm picking up an extra proton here in NH4+. So that proton from H2O has to be going over here to ammonia. And if that's the case, this makes NH3 my base and H2O my acid. So the conjugate pair to a base, right, NH4+, that's the conjugate pair. That's going to act as my conjugate acid in the reverse reaction. And for the acid, H2O, well, I'm creating OH minus. In the reverse reaction, that's going to act as a conjugate base, right? Because I could also write this reaction as NH4 plus OH minus, and that would make NH3 plus H2O. So what's got to happen there? Well, the proton has to go from here to here. That makes NH4 plus the acid and OH minus the base in the reverse reaction. So I can identify these pairs, and I can say, oh, ammonia and ammonium are base conjugate or conjugate pairs. NH3 is the base, NH4 is the conjugate acid. Water and OH minus are also conjugate pairs. Water is acting as the acid, and OH minus is acting as the conjugate base. All right. Now, just to go over Lewis theory in a little more detail and depth. It's a different perspective from Bronsted-Lowry. We're not looking at the hydrogen atom at all. According to Lewis' definition, the only thing we got to look at are electrons, and because of that, we don't have to have a hydrogen atom present in order to have a Lewis acid-base reaction. So this is really important for organic chemistry when you have Lewis acid-base reactions going on all the time for aprotic solvents. The electron donor is the Lewis base. This is known as a nucleophile in organic chemistry. So you'll hear this term in organic chemistry if you decide to take it with Dr. Kelleher, nucleophile. You keep in mind that a nucleophile is just a Lewis base. It's defined as an electron-rich center which donates electrons. A Lewis acid is something that accepts electrons, and if you're accepting electrons, that must mean that you're electron poor. And in organic chemistry, we call that an electrophile. So next year when they're talking about nucleophiles and electrophiles, we keep in mind that these are really just Lewis acids and bases, right? The nucleophile is the Lewis base. The electrophile is the Lewis acid. Okay, so the Lewis base has to have electrons it's willing to donate in order to be a strong Lewis base. And it must have a lone pair of electrons that it can donate. So it's got to have a lone pair of electrons, and it has to want to give those electrons to something else. So it makes sense then that anions are actually much better Lewis bases than neutral molecules. Something like N- is going to have more electrons there, so it's going to be more willing to give up its electrons than just a neutrally charged nitrogen. And also, generally, we see the more electronegative an atom is, the less willing it is to act as a Lewis base. So sulfur is a lot better at being a Lewis base than oxygen is, and that's because oxygen is more electronegative, so it kind of wants to keep its electrons. So electronegativity does play a role here. For Lewis acids, you have to have something that's electron deficient. And usually this happens when an atom's attached to a really electronegative atom, or it doesn't have an octet. And you also have to have an empty orbital willing to accept the electron pair. So for instance, H+, it serves as a really good Lewis acid because it has an empty 1s orbital. Boron and BF3, it has an empty 2p orbital. in an incomplete octet, so it can readily accept electrons there. It's a good Lewis acid. We see a lot of highly charged metal cations. They're really good Lewis acids. They have a high positive charge, so they really want electrons. They have orbitals they can put them in. And also, anything that's attached to electronegative atoms or has multiple bonds can act as a good Lewis acid. All right, so if we look at ammonia and boron trifluoride, we can identify what's acting as the Lewis acid and Lewis base. So in this reaction, we see that ammonia has this lone pair of electrons here, and that lone pair of electrons can be donated to boron because we know boron's electron poor, and we create one molecule. And so this molecule is known as a Lewis adduct. So anytime you have a reaction where you're taking two things and forming one new molecule, you can refer to it as a Lewis adduction, right? Because you're forming a Lewis adduct. This is still considered our Lewis base, and this is considered our Lewis acid. But notice we're not increasing the concentration of H3O plus or increasing the concentration of OH minus in solution. There's no proton being exchanged. So both of these substances, they act as, ammonia acts as a Lewis base here, but it's not acting as a Bronsted base, and it's not acting as an Arrhenius base. It only fits the definition of a Lewis base in this instance. So what we can say then is that Arrhenius and Bronsted-Lowry acid base reactions are also Lewis acid base reactions. However, right, Lewis acid base reactions do not always give you Bronsted or Arrhenius. So it can't be true in the other way. Bronsted and Arrhenius will always be Lewis, but Lewis will not necessarily be Bronsted and Arrhenius. All right, so here's some examples of some reactions that you might see. So I might give you something like this. Here you're looking at HCl, but we're no longer in water. We're in dimethyl ether now. And what happens is the electrons from oxygen will actually go and pick up that proton from chlorine. So HCl is acting as an electron acceptor, and the dimethyl ether is acting as an electron donor. That creates our Lewis adduct over on the right side. And so we could say this is our Lewis base. HCl is our Lewis acid in this instance. We already looked at this reaction where ammonia is the Lewis base and boron trifluoride is the Lewis acid, and we create this Lewis adduct on the other side. If we go back to that first reaction, what's the conjugate pairs? Well, if our Lewis base is that dimethyl ether, the conjugate acid is this protonated substance that we create over here, and our conjugate base is, of course, Cl-. We could look at other molecules such as a carbonyl. So a carbonyl is a molecule that has a C double bond O to it. And because you have this double bond here, let's go back. Because you have this double bond here connected to a really electronegative oxygen, it's going to be electron poor. And so the Lewis base can readily attack that. And you can kick electrons out and create this really interesting Lewis adduct. And this Lewis adduct we create on the other side is what's called a Zwitter ion. And it's a Zwitter ion because it contains both a positive charge and a negative charge that make it neutral overall. Right? So that's our Lewis base, that's our Lewis acid, and that's our adduct. The last example we're going to look at here is when you have a metal ion like silver. Silver plus 1 and ammonia, what happens is we create this complex, this Lewis adduct, where we have silver with two ammonias attached to it. And so silver in this instance is a metal ion, it's highly charged, so it's acting as our Lewis acid. Ammonia is a good base, Lewis base, and we create this Lewis adduct, which we also call a coordination compound. So Lewis adducts that contain a metal ion and a nonmetal are called coordination compounds. All right, we will end the lecture there today. Thanks for your attention. And when we return, we'll start talking about strong acids versus weak acids.